Thank you. Hi guys, how are you? Do you like coffee and cakes? Nice. Okay, my name is Mikhail Khludnev. I want to talk about joins in Lucene, about different joint implementation in Lucene. I work in company. Does it work somehow? I work in company Grid Dynamics. Our customers are American retailers. Our headquarters in Silicon Valley. We used to provide different engineering services for retailers. We do backend development. Now we do data analytics for internet advertisement. And I work in a team which delivers a search platform for e-commerce, for searching in product catalogs for customers. I'm a principal engineer. I spoke in last Lucene conferences. I made several little contributions into Solar code base. For example, I contributed the block join query parser and update flow for Solar, but it was just a prototype. And if you follow Solar Jira, you know that Uwe was really upset by the ad hoc, the way which Solar handles block join. So I'm really regret about it. My favorite contribution, most enjoying, was an attempt to fix threads in data import handler. Have you heard about data import handler in Solar? So you know there was this setting to enable multi-threading, but it's a little bit unstable. And when my fix was committed there in branch 3.x, committers decided to completely remove threads from data import handler. Right after I fix all concurrency bug during the long debug session. You know, I'm not sure how it depended with my contribution at all. Nobody told me, they just dropped it. So this is an advanced section. Session. That's why I expect that you are aware of how Lucene searches, how it applies updates by stacking segments one on each other, what is doc values, and why do you need to care about joins at all? Because it might be sort of specific question. You know, that many people use Lucene, Solar, Elastic, and don't care about joins. But I care, and I suppose that you share my concerns about joins. So here's the plan for today. I want to discuss existing implementation of join queries in Lucene and propose some new one. Okay, Lucene is pretty good and reliable and efficient in essential searching, filtering, and it's also pretty strong in analytics features. It starts from facets, and now Lucene and Solar have implementation for distributed pivot facets. For heat maps, it's pretty strong in analytics. It makes them pretty powerful tool set. But they still have a weakness. It's a robust join, so they still lack of universal, always efficient join algorithm. We have few of them, but we easily can face an edge case where some particular join query doesn't work well. And usually join looks like this. So that's what we have in relational databases. We have two entity types, and we have relations somehow declared between two entity types, for example, by equal keys. So one product ID is equal to another product ID. Before we look into particular implementation, I'd like to look onto this problem and to join operation in general. So let's depict one entity types by squares and second entity types by triangles. So it's our two entity types in the index or in database, whatever. Then we declare some predicate which actually define the relation. And this definition, which can be read by primary key is equal to foreign key. In fact, it defines the third set, the set of relation tuples. So we can draw it by this, by grouping the triangle and square, right, and get this little house. So our relation is a set of relation tuples. It looks like this. That's what we will work with in this talk. Let's also limit our discussion, our explanation by the typical case with one-to-many relation. We can call one entity types as parent and second entity types as children, and limit the relation to one-to-many case. So every parent can have several children, but not vice versa. And it allows us to group relational tuples into these multi-stored buildings. So it's like relational groups. It's just grouped relation tuples. So now we are ready to execute generic join operation. Usually it looks like this. We have a children side query or predicate which select some certain children entities. So while executing join operation, we need to loop through them and somehow obtain the relation tuples belongs to the children entities. And through the relation tuples, we can navigate to associated parents like this. And it seems like join operation is over. That only thing which we need to do, we just calculated associated parents from children. But in fact, in general form of join, we sometimes can have a second filter which is applied to parent side of join operation. It looks like this. And we also need to intersect the set of associated parents with this predicate, with this parent filter. And here you can spot the opportunity for optimization. So you see if the parent filter is highly selective, if it passes only few parents, there is not much sense to calculate all associated parents, right? In this case, you can employ this fact and start to execute join operation into the opposite direction. It looks like this. We can start from looping our few parents and just navigate through relation tuples to the associated children and check them for intersection with the given children filter. I think that's enough for this level of generality. So I want to summarize that join operation is the intersection of three sets of parents, sets of children, and join relation. Where sets of parents and children we are provided in query time. So every time we get the new subset of children and parents, and join relation is more static. It's defined by data. So our data forms the join relation set. And one note about join relation set, that some algorithm might not even build these tuples, these relation tuples. Some implementation, for example, like nested loops join, calculate these relation tuples like dynamically during nested loop, like this. And depending on the particular business problem, we might need to output different side of join operations. sometimes we need to return only parents, sometimes we need to return only children, or even sometimes we need to return both of them grouped together. But nevertheless, it's up to us to choose proper direction for enumeration. So considering the particular selectivity, particular set cardinality, we can loop through children or through parents. It's up to us. We can mind the computational efficiency here. So now it's time to look at the first implementation. It's a query time join, which is implemented in class joinUtil. It uses doc values, just special data type where we need to store our IDs. So the parent IDs is stored in doc values column. So what it does, it loops through children, which are called it's from side of join. It obtains the value of parent ID for every children and drop them into accumulator in this set of terms. So that's what it does. It just scans children and collect parent IDs. And the second stage of join operation is searching for the occurred parent IDs. It's done like regular term queries. So in fact, query time join execute term queries from the seen parent IDs many times. So the more results you have, the more operation you do. And there is one problem with it, that Lucene term dictionary is not built for doing frequent term lookups. It's a little bit expensive operation. And it's the main problem with query time join. So we discuss it a little bit later once again. Now we obtain parent documents, and we can intersect them with parent predicate. Here's the second implementation, which is block join. Block join is a quite clever idea. It utilizes the fact that Lucene models document with document numbers. So it assigns numbers to the document, and it allows a certain type of natural relation between documents. So in Lucene internally, documents are not just identified, they assign numbers. So we can employ this relation between numbers. We can say which documents comes after another. And what actually block join does. Our documents are numbered, so we can just index them in blocks or in groups and just put every parent right after their children. And Lucene provides special API for them, and what it does is just assign internal numbers consequently on children, and the parent goes right after them. It looks like this. Then in query time, we can obtain this information about parents in form of simple bit set, and it allows us to navigate from children to parents. It looks like this. We loop through children documents, and with simple bit set scanning, we can navigate to the parent belongs to these children. That's what it can continue to find all associated parents, but in fact, it does more efficient thing. Lucene has an algorithm which is called leapfrog for intersecting queries, for executing conjunction query, and it's done in really efficient way. So what it can done here, instead of looping all parents by the same direction, Lucene can realize that many associated parents are really redundant, and we don't need to obtain them, and it can advance children's side of join operation over unnecessary parents. Right, so this algorithm is already in Lucene. It's called leapfrog. So the most selective side of join operation start to lead join operation, avoiding unnecessary step. It's really performance breakthrough. So Lucene does it, advances children's side of join operation, and now it can continue to do this from the first children of the parent which matches the given parent filter. Something like that. Okay, let's summarize, let's break down the comparative performance of this join implementation. Searching by query time join is slow, and the question is why it's so slow. And there are two reasons. The reason number one, because it calls expensive operation of term lookup many times. So it's not what Lucene term dictionary was created for. And the second problem is that it always loops through all children and then search for parents. Then even you supply highly selective parent filter, it cannot anyhow speed up the join operation. These are two issues with the current join util query time join. And block join, which is index time join, is pretty fast, right? Because it doesn't hit any expensive data structure, it doesn't hit any expensive operation, it's just pretty lightweight, and always it utilizes the leapfrog algorithm to execute join operation in the most efficient way. And more than that, you don't need to care about selectivity of the filtering statements. Lucene does it for you automatically, and it's perfect. There is some cost in indexing side. The most often question about join, what do I need to do if I need to update some entities in join operation? So in case of query time join, you need to bother about it at all. There is zero index time burden, right? It just costs you nothing. And in block join, there is an issue, right? Because you need to establish, you need to keep this constraint of blocked index. You cannot just reindex single children, right? You need to reindex whole block. And it might seem not as a big deal at all, because Lucene is quite performant in index time. And for example, we can say that there is no difference in reindexing performance between single document and between reindexing 10 document. It's really hard to evidence the difference between cost of this reindexing. But in some edge cases, for example, if you have really huge blocks, right, it might be a big problem. So as I said, you always need to enlarge the scope of index update. And for example, if your blocks are really huge, for example, 1,000 document, then instead of updating, let's say, 1,000 of children, you need to reindex all their block, and you might end up with updating millions of documents. It might be sensible cost. And the second problem with it, that from just system design, it is not convenient property at all. What we have, usually we have separate system which runs some sort of business process, react to events, and search engine. And business process just want to tell our indexing part, just please reindex one document, I have some changes. And with the block join design, search engines need somehow realize what is the source data for nearby documents, right? It usually need to call the document storage for the sibling documents, and in some architectures it is not what we can afford. I have one more concern about block join regarding query time, but I feel it's a little bit subtle concern, so I want to skip it for now. Let's discuss it somewhere later. So block join is perfect in query time. So, and I tried to find the algorithm, to develop the algorithm which will be somewhere in the middle, right? Because it's not possible to be faster than block join, right? That's what I try to pursue in my research. And the idea was to provide join index in Lucene. The idea is straightforward. I want to use the same doc values column, but I wish to put not external IDs in this column, but I want to put document numbers in it. Now I don't need to run the expensive step of resolving the external IDs to doc numbers. So I just need to put the doc numbers of the associated parents in doc values column. But there's a problem that because it's not even it's not possible in Lucene API right now. I cannot supply document numbers as a source data of my documents. That's why I find the workaround. I apply updates in 2 stages. So first I index the source data, and then I apply join index to this column by updatable doc values. So I can reindex whole column. It's a recent feature in Lucene. And if I'm able to do that and put document numbers of the associated parents in doc values, now the join is pretty straightforward. I need to loop through children documents and just collect parent document numbers. Then I have to sort it. Now it's mandatory step because recently out-of-order collecting was prohibited in Lucene. So, but nevertheless, the process of join operation is quite simple with this index. Then we just sort associated parent IDs and intersect with parent filter. But more than that, here is an opportunity. If we use binary doc values, we can put a whole list of associated children in the cell of binary doc values column. And now we have an opportunity to start join operation on opposite way, on more efficient way, if we have highly selective filter like this. Then we need to just loop through few parents and check the associated children for intersection with the given children filter, and drop the parents into result if they intersect. Okay, I spoke about this prototype at autumn, and recently I found quite interesting Jira. It's about backporting global ordinal query time join from Elasticsearch to Lucene. It is pretty interesting. It's a shame on me that I didn't know about it. So let's look into it. It's a pretty interesting thing. It's called global ordinal query time join. So it works almost like query time join, but it uses sorted doc values. Do you know what the feature in sorted doc values, why it's necessary? Do you know about them? So they was developed for providing sorting by field value. For example, if you need to sort your documents by some product name, for example. In this case, instead of sorting by strings, because comparing strings is expensive operation, during index time, for every such column, Lucene builds separate index where it collects all values from this column, deduplicates them, sorts them, and assign ordinal numbers. And then it stores these numbers in the column. And right now, if we need to sort by this column, we can compare numbers and sort by numbers, which is quite cheaper than comparing strings. So, and this query utilizes this pretty cool structure. What it does, it loops children and obtains the associated ordinal numbers of parent keys, something like this. And it also drops them into accumulator, but in case of ordinals, accumulator is pretty straightforward. It's just a bit set. It's much more compact and efficient data structure. And at this second stage, it loops through parents and does the same thing. It obtains the ordinal number of the parent key and check the bit set for intersection. That's how it recognizes that any of the children has the same value of the parent key. So, and now let's compare all the implementations. Here's a URL to Lucene fork, where I put my implementation of join index query, and where I extended the Lucene benchmark module to benchmark join algorithms. These are not great hardness, but it works and does what we need. So I'm able to run pretty fast benchmarks for all these queries. So what we see here, block join outperforms query time join, and it's what we expect. But it's worth to mention that benchmark is not really representative. What I evidence at practice, that block join outperforms query time join at orders of magnitude. So it's way faster. It's more faster than several times. Might be faster than 10 times and even more. Nevertheless, these small benchmarks show us something which is related to the practice. Now you can see that join index performs pretty well. It performs better than join util. And here it seems like join index faster than global ordinals query. It's not correct. It's not true. Because I had to apply updates for join index in quite rarely. So all these three queries from Lucene benchmarked by frequent updates by 2 times per second, and I have to apply updates to join index in much lower rate because of the problem with updates, which I will discuss later. So what we see, that join index is a perspective idea, but there is a big problem with it. Right now I cannot apply updates incrementally. But we also see that global ordinals query, it's a great and performant query time join, and I quite recommend it to use instead of plain old query time join. Okay, here is a comparison chart. Join index fast and global ordinals query also fast, but block join faster anyway, because block join can join in both direction. So it joins in most efficient way, and it joins themselves. You don't need to choose the efficient way for enumeration. Okay, global ordinals has almost zero cost for update, and there is a big problem with applying updates on join index. The reason is that just for simplicity, just make simple prototype, I fully recalculate the full column of join index every time you apply any update. So I didn't reach the initial aim I'm somewhere in the middle of the way. But it's proved a general idea, and I still consider it as perspective. And here a revised plan. I plan to work in incremental join index update. I think it's possible. That will allow us to join in both directions to execute join operation in the most efficient way, which is not possible in a global ordinals join so far. And I need to upscale the benchmark to highlight the hardest, the weakest kinds of every implementation. So current benchmark is too small to represent any real challenges for queries. That's all from me for today. We've looked into join implementations. We've looked into join problem in general. I gave you an example of how you can use updatable doc values, but it's not the proper way to use them, but I recommend them for using in your application. It's pretty interesting feature. And there was some ideas for speeding up query time join if you struggle with its performance, but now they are all legacy and obsolete. They don't have much sense. Now I can recommend to use global ordinals join if you need fast query time join. Here are a few references if you want to go deeper in this and all these problems. And here is a shortcut to access the slides if you wish. So now I'm open for questions. We have some time left. Okay, you are welcome.
All right, let's take questions and thank the speaker.
Thank you. Thanks for your time.